Welcome back. This video presents section 1.7 in your textbook. The section introduces the idea of a linearly independent set, which connects closely with the concepts of linear combination and span first introduced in the section 1.3, as well as parameterization of solution sets to homogeneous systems that you just learned about in section 1.5. Let's get started. Suppose you need to get from point A, right in front of the park bench, to point B, which is in front of the garage door. If you are thinking about some rules you might have heard as a child, the ones about sticking with the sidewalks, a natural course would be to walk through 2U along the pink vectors and then through V along the blue vector. If you are feeling more adventurous and are willing to walk through the grass, you could get from A to B by walking through W instead. It might be nice to walk through W, but it isn't necessary. You can get from A to B by moving only in the direction of U and V. In some sense, W is extra. You can form it as a linear combination of U and V. Informally, we say that a set of two or more vectors is linearly independent if it contains only essential vectors. That is, if none of the vectors in the set can be written as linear combinations of the other vectors in the set. If we use our intuition that each vector in a linearly independent set describes a new direction that can't be built from the other vectors in the set, we might think that any set of a single vector would be linearly independent. But we'd be forgetting that the zero vector doesn't describe any direction. A set containing only one vector, say V, is linearly independent if and only if that vector is not the zero vector. In fact, any set that contains the zero vector, no matter how many other vectors it contains, is not linearly independent. We call such sets linearly dependent. The zero vector is extra, like W was in our example previously. It doesn't let you get anywhere new. Now, let's move on to sets of two vectors. Again, informally, we can say a set of two vectors is linearly independent if it contains only essential vectors. That is, if none of the vectors in the set can be formed as linear combinations of the other vectors in the set. Looking at the two vectors pictured here, we can see that U isn't a scalar multiple of V because U doesn't lie on the same line as V. This means that U can't be written as a linear combination of the other vector in the set UV. Similarly, V isn't a scalar multiple of U. Summarizing, U and V do not lie on the same line, which means neither is a scalar multiple of the other. This means that the set UV is linearly independent. Be careful here. With only two vectors, writing one vector as a linear combination of the others means writing that vector as a scalar multiple of the only other vector in the set. As our sets get larger, linear combinations will not have to be scalar multiples. This characterization is specific to sets of two vectors, but it's still worth remembering. Now, we'll look at a set of three vectors. This gives us enough space that we can make some generalizations to n vectors as well. In this example, V and W lie on the same line. Since U is not on that line, I can't write U as a linear combination of V and W. But this does not mean that the set UVW is linearly independent. For the set of three vectors to be linearly independent, it would need to be the case that none of the vectors could be written as linear combinations of the others. W is a linear combination of V and U. It's just -1 times V, so we can write W equals -1V plus 0U. This means the set UVW is not linearly independent, it is linearly dependent. We're going to look at the maple file that is linked in the H5P description for this H5P video. First, we'll ask if we can change U to make UVW a linearly independent set. Then we'll ask if we can change V to make UVW a linearly independent set. This maple file is linked in the description of this H5P video. We are talking about investigating linear independence or dependence of a set of three vectors. These are the vectors v, w, and u that we talked about in the video before. The first question we were asked is, could we change u in a way that makes u, v, and w a linearly independent set? But as we said in the video, and is maybe even more apparent now that we can move the graph around, we can see that v and w lie on the same line. W is just -1 times v. You can also say it's -1 times v plus 0u. It doesn't matter what u is, -1 times v plus 0u is still the same thing, and that's w. So no, it doesn't matter what we do with u, w will still be -1 times v plus 0u. So we still have that linear dependence. Next, we were asked, well, could we change v in such a way to make u, v, and w linearly independent? So again, these are the vectors u, v, and w, and I've just added one thing to the plot. I've added the plane that's spanned by u and w. So this light blue plane represents all of the linear combinations of u and w. And right now, you can see that v is in that plane, which means that v is a linear combination of u and w. So we're asked, well, can we get v out of that plane so that it's not a linear combination of u and w? Let's make a change. So I'm just changing a v to 2t, 5t, maybe -3t. And then I'm going to look, and yes, v is out of the plane, which means that v is not in the span of u and w. That says that v is not a linear combination of u and w. And you can similarly check that u is not a linear combination of v and w, and that w is not a linear combination of u and v. And we have a linearly independent set. We may not be able to use geometric intuition to help us in higher dimensions. How can we tell algebraically if a set of vectors is linearly dependent? Let's again think about three vectors, but these ideas will generalize to any size set. We just saw that if we want to see if a set of three vectors is linearly dependent, we need to ask if each vector can be written as a linear combination of the other two. This translates into three vector equations that need to be solved. That is tedious. And if we had more vectors, we'd have more equations and more work. Can we reimagine the three equations so that they look more similar? Yes! We'll rearrange the terms so that each is a homogeneous equation expressing the zero vector as a linear combination of the vectors u, v, and w. Now we can think of each as a homogeneous equation of the form a1u plus a2v plus a3w equals the zero vector. The first question in our last column is asking if we can find a non-trivial solution with a non-zero value for a1, because then we could scale that to become a1 equals -1. The second is asking if we can find a non-trivial solution with a2 non-zero, and the third is asking if we can find a non-trivial solution with a3 non-zero. Putting these together, they are simply asking if we can find a non-trivial solution to the homogeneous system a1u plus a2v plus a3w equals the zero vector. If we can, then the vectors are linearly dependent. If we can't, then the vectors are linearly independent. This leads to our formal definitions of linear independence and linear dependence. A set of vectors v1 through vp is said to be linearly independent if the only way to write the zero vector as a linear combination of the vectors in the set is trivially, with all of the coefficients being zero. The set is linearly dependent if you can write the zero vector as a linear combination of the vectors in the set non-trivially, using weights that are not all zero. Next, we'll ask ourselves if the vectors 3, -3, 6, 5, -2, 1, and 7, -1, -4 are linearly independent. We can see by inspection that none of the vectors are multiples of the others. But since we have three vectors, this is not enough to say that they are linearly independent. One could be a linear combination of the others without being a multiple of the others. We need to use the definition of linear independence to check. The definition says we need to check to see if the only way to write the zero vector as a linear combination of the three vectors is trivially, with C1, C2, and C3 all zero. If the answer is yes, then the vectors are linearly independent. If the answer is no, then they are dependent. We can rephrase this in terms of a matrix equation. We want to know if this equation has only the trivial solution. We know the trivial solution is always a solution to every homogeneous system. This means that asking if the equation has only the trivial solution is equivalent to asking if it has a unique solution. So now we're asking, does the system have a unique solution? If the answer is yes, then the vectors are linearly independent. If the answer is no, then the vectors are linearly dependent. Let's look at the row echelon form to find out. I used Gaussian elimination in Maple and discovered that the row echelon form has 2 pivots. The system has 3 unknowns, and with just 2 pivots, this means we must have a free variable. Therefore, the system has infinitely many solutions, and the set of vectors is not linearly independent. It is a linearly dependent set. Let's investigate this system further to find a parametric description of its solution set. To do this, we'll reduce further to reduced row echelon form. We can then translate the reduced row echelon form back to a system of equations. The first row tells us that C1 minus C3 is equal to 0, and the second row tells us that C2 plus 2C3 is equal to 0. Since C3 is free, we assign it a parameter, say C3 equals T. Then, substituting this into the first equation and solving for C1 gives C1 equals T. And substituting C3 equals T into the second equation and solving for C2 gives C2 equals negative 2T. Finally, we can factor out the T to give a vector form of the parametric solution.
To review, we wanted to know if the vectors 3, negative 3, 6, 5, negative 2, 1, and 7, negative 1, negative 4 were linearly independent. We did this by looking at an arbitrary linear combination of the 3 vectors with weights C1, C2, and C3, and seeing when this linear combination can be equal to the 0 vector. If the only way to make it 0 is to choose all weights to be 0, then the vectors are linearly independent. If there is a non-zero solution, then the vectors are linearly dependent. Since choosing all weights to be 0 is always a solution to the homogeneous system, we know that the vectors are linearly independent if and only if this vector equation has a unique solution, necessarily the trivial one. And the vectors are linearly dependent if and only if this vector equation has an infinite number of solutions. So we looked at the equation in matrix form, used Gaussian elimination, and found out that the system had an infinite number of solutions. Any point on the line with parametric equation 1, negative 2, 1 times t was a solution to the system. This meant that the vectors were linearly dependent. We can see a few specific ways to write the 0 vector as a non-zero linear combination of the 3 vectors by simply choosing specific values for t. If t equals 1, then C1 is 1, C2 is negative 2, and C3 is 1. So we have 1 times the vector 3, negative 3, 6, minus 2 times the vector 5, negative 2, 1, plus 1 times the vector 7, negative 1, negative 4 is equal to the 0 vector. If t equals 2, then C1 is 2, C2 is negative 4, and C3 is 2, leading to a second way to write the 0 vector as a linear combination of the 3 vectors. The specific ways to write the 0 vector as a non-trivial linear combination of a set of vectors in a set are called linear dependence relations for that set. Let's look more closely at the first linear dependence relation, the one with t equal to 1. We could solve this relation for the vector 7, negative 1, negative 4 to see a way to write the vector 7, negative 1, negative 4 as a linear combination of the other vectors in the set, tying back to our original characterization of linear dependence. We can see now that the vector 7, negative 1, negative 4 is in some sense extra because it can be formed as a linear combination of the others in the set.
In our next example, we consider a matrix with an unknown entry and ask, what does this entry H need to be so that the columns of the matrix A are linearly independent? Going back to the formal definition, we're asking for which values of H does the vector equation C1 times the first column of A plus C2 times the second column of A plus C3 times the third column of A plus C4 times the fourth column of A equal to the zero vector have only the trivial solution. We can rewrite this as a matrix equation, and again, because the trivial solution always works, asking if the system has only the trivial solution is asking if the system has a unique solution. Since we have four unknowns, C1, C2, C3, and C4, we must have four pivots to create a unique solution. Therefore, we need H plus 2, highlighted in blue, to be non-zero so that it will be our fourth pivot. This means that the columns of A are linearly independent exactly when H is not equal to -2. In our last example, we'll ask several questions about the given matrix A. First, how can we tell by inspection, without any calculations, that the columns of A are linearly dependent? When we set up the corresponding augmented matrix for the homogeneous system, we will have at most 3 pivots, 1 for each row of A. However, A has 6 columns, and so we would have 6 weights. This means we would have at least 3 free variables. Therefore, the columns of A are linearly dependent. In fact, if you have a set of more than n vectors in Rn, the set will always be linearly dependent for this exact reason. The next part of this question asks us to give an example of a linearly independent set containing as many of the columns of A as possible. Think about which columns of A we should keep and which we should eliminate so that the matrix equation Ax equals the zero vector has only the trivial solution. We can tell by looking at the reduced row echelon form of A. In order to have a unique solution, we need a pivot in each column of the coefficient matrix A. This means I should keep the first, third, and fifth columns since they will have pivots in the reduced row echelon form. Therefore, the set containing the first, third, and fifth columns of A is an example of a set containing the maximum number of linearly independent columns of the matrix. Finally, we're asked to write the columns of A that are not in the set we just gave as linear combinations of those that are. We already have all of the information that we need for this. Let's take those columns that are not in our set S one at a time. First, think about the vector 0, 12, 4. You can probably just see that this vector is 4 times the first column of the matrix A, but I wanted to run through this algebraically as well. Because the reduced row echelon form has pivots that indent from left to right, we can actually write any linearly dependent column of A as a linear combination of the columns to the left of it in the matrix. For this reason, I'm going to totally ignore the columns to the right of my vector 0, 12, 4. I've put them in light gray to indicate that they've been ignored. I'm solving the system C1 times the first column of A in orange is equal to the second column of A in blue, and the reduced row echelon form says that C1 equals 4. Therefore, the second column is equal to 4 times the first. Now, let's think about writing the fourth column, 6, 3, 1, as a linear combination of the linearly independent columns that come before it in the matrix A. I'm trying to solve the system C1 times the first column of A plus C2 times the third column of A, both in orange, equal to the fourth column of A in blue. I don't need to worry about the second column of A because it isn't in my linearly independent set, so I've grayed it out as well. The reduced row echelon form says C1 is -2 and C2 is 1. Therefore, the fourth column of A is -2 times the first column plus 1 times the third column. Or the sixth column of A is equal to 4 times the first column plus 5 times the third column plus -1 times the fifth column. The equations that we found in part C each correspond to a linear dependence relation for the columns of A. That concludes our discussion of section 1.7. You probably noticed that we used all the tools that we've built up so far in our exploration of linear independence. That makes this a great section to end our module.